2.1 galvanic cells. Okay, now we want to see what is the galvanic cells. If you have two solutions and it's connected by a bridge, this bridge could be a salt bridge or any solution, and it's divided by kind of a cloth or a product. So from here, the ions can move from the solution to the other solution to balance the charges. So whatever we have solution here, we call it electrolyte here. On the other one, we have electrolytes also. We have cotton plugs there. For example, if you have a CuNO3 as a solution here, and the Cu will be a rod. I just want to show you here. The copper. Copper is your electrode. The Cu is the electrode here. Solution is CuNO3. And on the other one, we have ZnO3 and Zn. Zn is zinc, is a rod, and ZnO3 is a solution, and here is a salt bridge. So here is zinc is electrode, and the solution is electrolyte. So this is half cell, this is another half cell. And you know that the electron will transfer from Cu to Ag. Now, why that happened? If you look at the oxidizing agent and reducing agent, Cu and Ag. Look at, I just want to look at that again, Cu and Ag, right? Cu is here, Cu2 plus, and Ag is there. So Ag is the strongest oxidizing agent. Oxidizing agent means it receive electron, right? So Ag will receive electron and Cu will give off electron. So Ag is the strongest oxidizing agent, stronger than Cu. So when it is oxidizing agent, the reduction will happen in there. And if this is the strongest reducing agent, oxidation will happen. Oxidation means give off electrons. So electron from Cu travel to the Ag. Now, what is actually happening in this situation? Since the electron is traveling, you need this Cu losing the electron, right? Losing electron travel here, and the Cu2 positive will be released in this situation. Because it had Cu, the electron was taken off from that. Now it becomes Cu2 plus, and it's coming to the solution. Electrons travel here, go to the Ag. Now Ag need to get that. We have an Ag plus here. This will attach itself to the rod and absorb that electron, become Ag as a solid. The solid Ag will be produced around this rod. So what is happening here? Because now the Cu2 plus is released into the solution here. We have too many positive Cu ion here, right? So it cannot be continued. We have to really balance the Cu build up around this rod. What is happening? This salt bridge help us. From that, NO3, the negative ion, will travel here, cancel some of those positive charges on solution. And also here, Ag attached itself here, now negative. You have a negative ion build up here. That's why a positive ion from here, which is Na plus, will travel. Na plus will travel here. Na plus in the salt bridge, travel into that. Make sure that this negative ions building around your cathode will be balanced, and this can continue. And as you know, the Ag will get an electron, become Ag solid around that, and here Cu lose electron, so it becomes Cu2 plus. So you have a 2 plus. I'm just going to correct that. So it's just going to be 2 plus positive on the top of that. the one that is the electron moving from anode to the cathode. So the negative side is the positive side. And as you see, we can write it as Ag plus. So this is the strongest oxidizing agent. This is oxidate. This is the reduction agent, right? The strongest reduction agent is Cu. So Ag plus electron give you Ag, and Cu plus 2. Since it's 2 electrons is electrons, so you need to multiply this one by 2 to balance the charges. So you multiply by 2, you add the right side, left side, the electron cancels on both sides, and this is the result of this cell reaction we have. First, if you want to write the cell, here you put your cathode, here you put your anode, or this is reduction happen, here is oxidation. Oxidation happen. And you need to know the direction of the cation and anions when the question is given to you and ask you to do that. So galvanic cells with the inert electrode. So sometimes we could have an acid as your cathode. That's why, because the H will really react here. You need an inert, electrodes like a C here. The C will not react. It's just there to transfer electron from the solution, right? And here is Cu. So if you look at the chart, we have CR7, we have this acid, we have Cu. Let's see which one is the strongest. So here is CR207, we have that, we have Cu here, of course. CR207H will be your strongest oxidation agent. So this is going to be your cathode, and now this is going to be your anode. So your cathode will be, you just write the reaction, and anode should be Cu, right? So here the reduction happen here and oxidation happen here. So it's losing electrons, gaining electron. Here to write these two reactions, you can look at the reaction here on this table and write the same thing you see. For Cu, you have to do it reverse, right? Because Cu is going to be your strongest reducing agent. Therefore, you just want to balance the charges. This is 2 electrons, this is 6 electrons. You multiply everything by 3 to make this one 6 electrons. And add up right side, add up left side, and this is what you have for the reaction. And as you see, the electron from anode travel to the cathode. It's from Cu, electron traveling to the cathode. And since the Cu, you have a positive charge released from the Cu, right? Then you need an ion to come here to cancel the positive charges. And here, the negative charges will be built up here on the solution, so the cation need to come and go. So you need to know the direction of the cation and ion is important. Now, standard cell and cell potential. So I want to see what is the cell potential. If you have, you want to find the potential difference across cells, because then now we have a current, there will be a potential difference across your cathode and anode. We can use a voltmeter to measure that, and here will be the potential change. It's going to be potential on cathode minus the potential on anode. So the potential for hydrogen is going to be 0. This is your reference. As you see in this table, the potential of hydrogen is 0, and everything above that is positive, and below that is negative, for all of this reaction is written. So we can use that table to find the actual potential difference across that. So for example, for CuH, so PT, so when we have that, the Cu will be your cathode and H will be your anode. So you know it's cathode minus anode. So writing the cathode here, the cathode is Cu, right? Cu is 0.34 minus the anode, which is hydrogen, is 0. So 0.34 minus 0 is 0.34. here you can have just written precise things. So Cu you have, H you have, this is your cathode, this is your anode. You add them up, so your cathode in the table is 0.34. For hydrogen is 0. If you look at the table and do the minus, then it's 0.30. So here is again for hydrogen and for Al, you look at the table. This is your hydrogen and here is the Al. Of course, the Al will be, the hydrogen will be your oxidizing agent. So the reduction happened there. This is your cathode and this is going to be your anode. So the cathode minus anode 0 minus 1.66 is 1.66, as you see in detail here. So this is your cathode, right? It's 0, and here is your anode with negative 1.66. So 0 minus 1.66 is 1.66. And here, this is depicted here on the table. We have hydrogen above the Al, and we have investigated that before. If your delta E is positive, when you find it, this indicate that the net reaction is a spontaneous, a requirement for all galvanic cells. Look at this standard dichromate lead cell is constructed. Write the cell notation, label electrodes, and cathode standard cell. So dichromate is an acid, right? So standard dichromate lead. Lead Pb and Cr2O7. So we need to have a carbon here because this one is reacting, very reactive. We need to have something inert. So this is what we have. So we need to look at that and Pb on this. So this is Cr. And where is the Pb? Pb is here. Of course, the chromate's gonna be your cathode, and the Pb are gonna be your anode. So cathode minus anode. So what is the value? Is 1.23 minus negative 0.13. 0.30 minus negative 0.13, and this is will be your change, the potential difference. The standard copper scandium. So this is copper, this is scandium. So again, look at the Cu and the C. Oh, actually, here is constructed. This is the delta E of the cell is given to you. Write and label half reaction net equation. We do not know for the scandium, right? We know the copper from the table. Again, I'm just going to bring it out. So this is copper positive 2 is the what? Almost there. Cu2 positive there. 0.34, right? Here for Cu 0.34. We do not know what is for scandium, right? And this is the question mark. And this is for total reaction. We know cathode minus anode. So 0.34 minus the things we don't know equal to that. We just finding the E for scandium. So it's going to be negative 2.02. This is what we write.